Hello guys, today we're going to have a quick review of 1.5. We saw most of this last year, so it's going to be a short video detailing transformations. Now, in page 45, you can see the basic parent functions. You should remember the names and the shapes. Constant, linear, quadratic, cubic, square root, reciprocal, absolute value. Make sure you remember all the basic shapes. You should already know these. Review them on page 45. Next, it says, describe the characteristics of a parent function. You should by now be able to do the following. State the domain and range. State the intercepts of the graph, both x and y, if any. State the symmetry, which is symmetric across the x, symmetric across the y, or symmetric across the origin. Visually, you can do this easily. Mathematically, not so much. At least try to recognize it visually. Also, whether the graph is continuous throughout all its values of its domain or not. Pretty much if the graph begins somewhere, like a square root, where does it begin? And also where the graph is increasing or decreasing. So again, basic shapes and basic characteristics of the graph. Next, we're going to focus on vertical and horizontal transformations. First of all, let's just focus on the quadratic or cubic or any function. When you add outside of the function or subtract, this would move the quadratic upward, this would move the quadratic downward. X squared minus 1. If you want to shift something left or right, you have to place it within the parent function. So for example, this is a quadratic that has moved 1 unit to the right. It's the opposite. And this is a quadratic that has been moved 1 unit to the left. It's opposite, remember, because the formula is x minus h squared plus k. If you put, this is the basic mathematical formula. If you plug in a positive value, like 1 to the right, it would appear negative. So it looks negative, but it's actually 1 to the right. If you plug in a negative number, like -2, and you multiply by negative, it will become +2. So you're actually plugging in a negative number, but it looks positive. That's why it's the inverse, okay? Outside up, outside down, inside, it's the opposite, right? Inside, it's opposite to the left. Now note, this works pretty much any equation. If I have square root of x, this would move it upward. This would move it to the left. Outside versus inside. It applies to any basic parent function. We saw this last year, so that's just a quick refresher. So that takes care of up or down. Now let's go over vertical and horizontal dilations. If this is your parent function, if you multiply outside, it would be vertical. If you multiply inside, it would be horizontal. Now note, it could be either a stretch or a compression, also known as shrink. Now, when you're focusing on the outside, pretty much like the up or down, it more or less makes sense. Outside is up, outside is down here. This is a stretch, and this is a shrink. A number between greater than 0, smaller than 1, a number greater than 1. So again, a bigger number, it makes sense that this is a stretch. Vertical, because it's on the outside. A smaller number, it's on the outside, it makes sense this would be a vertical compression or vertical shrink. Now inside, everything is the opposite, pretty much like plus or minus. This would actually be a horizontal shrink or compression. It's the opposite, bigger numbers shrink you. And this would be a horizontal stretch, pulls the graph outward. Now remember, let's focus on an absolute value function. This would move it up, this would move it down to one side or the other. Okay. Now remember, A vertical, that, up or down, left or right, is pretty easy because the shape doesn't change. You just move the graph around. Vertical and horizontal is similar because in some cases, a vertical stretch is like pulling a rubber band upward, might seem similar to a horizontal shrink because it's kind of squeezing. So it's not the exact same thing, but it behaves more or less the same. And at the same time, a vertical compression, when you squash the absolute value, is similar to a horizontal stretch. So they are similar, not identical. Mathematically, we'll get different values, but the graph might look more or less the same. And to finish off example 5, when they're asking you to draw the piecewise function, the best way to draw a piecewise function without using Desmos or a graphing calculator is pretty much put like invisible lines where your breakpoints are. So say, for example, this is -1 and this is 2. Let's say you have 3 different rules. When x is less than or equal to -1, when x is between -1 and 2, and when x is greater or equal to 2. All you have to do is graph the type of equation. From this point on, I would draw whatever equation is up here. Between these two values, I would draw between those two values whatever behavior I have, if it's a constant, a quadratic, a linear, whatever. And from this point on, I would graph the last rule. And that's pretty much how you graph piecewise functions. So again, this is a very quick crash course. We saw a lot of this last year, so that's why this is just a small review. Take care.